Hi, my name is Ayan Lateef, and my project is using economic indicators as a factor for a predictive model to estimate potential future pollution for developing nations. In the 21st century, climate change has become a growing concern. We are starting to see changes to the planet that will soon become irreversible. Air pollution specifically is a growing health concern and a huge contributor to climate change. It causes almost 7 million premature deaths a year and affects 80% of people near urban centers. With many developing countries undergoing rapid industrialization, it is important to monitor air pollution and CO2 emissions. China alone has doubled CO2 emissions since 1990. While many countries cite economic gain to their disregard of their CO2 emissions, in the long run, climate change can potentially devastate economies. It's important to realize this problem is not confined within any borders and that in the fight against climate change, information is key. In my project, I used explanatory variables to predict the response variable. The independent variables used to predict the dependent variable, which was CO2 emissions, were HDI, GDP per capita, manufacturing output, income per capita, and population growth rate. Then I randomly selected 30 countries of which I was able to gather comprehensive data for 28 of them for the period of 1990 to 2018. After compiling and cleaning the data in Excel, I then inputted the data as data frames into RStudio, where I further refined it in order to run statistical tests and create two types of predictive models: a multiple linear regression model and a Bayesian model. The study was successful in creating a predictive model that forecasted the CO2 emissions in metric tons per capita for a given country with those independent variables and also predicting that China would reach 7.697 metric tons per capita of CO2 emissions, while the actual emissions were 7.95 metric tons per capita. This confirmed that the model was significant and the study was successful. The null hypothesis was that the data points of the five independent variables would not yield significance and therefore could not be used to produce an accurate predictive model, while the alternative hypothesis was that the data points of the five independent variables would yield significance and would yield a accurate predictive model for a given nation. The first step in my project was creating a dataset. I went through publicly available databases and compiled data for 28 countries. I then plotted histograms that compared the dependent variable with various independent variables. This was in order to ensure that I could use Gaussian mathematics with the data. I checked for normal distributions using analysis of the histograms and summary statistics. First, I created a multiple linear regression to model the relationship between various independent variables and a dependent variable by fitting a linear equation to the data. I used forward selection and backwards elimination as necessary in order to create a parsimonious model. In order to create data frames, process data, and create the multiple linear regression model, I used R, a language for statistical computing and graphics software. In R, the function lm was used to build a linear model. With the full model, I analyzed the p-values and adjusted r squared to drop any variables and optimize the statistical significance of the model. Next, I looked at the ratio between the variance of the model with multiple terms and the variance of the model with one term alone, also known as the variance inflation factor, in order to determine collinearity in the variables. If collinearity was present, it must be accounted for. To create a multiple linear regression model, four conditions must be satisfied. Each independent variable must be linearly related to the dependent variable. Residuals must be distributed nearly normal with a mean of 0. Variability of residuals needs to be nearly constant, and the residuals need to be independent. If these four conditions are met, then the model is parsimonious. Next, I created a Bayesian model. The Bayes factor, or the ratio of the likelihood probability of the null and alternative hypothesis, was calculated using the BAS function in R. The higher the Bayes factor is, the more likely it is for the alternative hypothesis to be true, while the lower the Bayes factor, the more likely the null hypothesis is true. I set the Zellner-Cauchy probability distribution, the uniform prior for the model, and Markov chain Monte Carlo method all as parameters to create a Bayesian linear model. In order to see the top 5 models that had 0-1 indicators for variable inclusion, I used the marginal inclusion probabilities from the model and examined the data using the summary function. Then I used the log posterior odds and model rank to see which variables would be best to include for an accurate model. Finally, marginal distributions and variable coefficients were examined using coefficient estimates and STD under Bayesian model average. The significance of the model was demonstrated by plotting residual versus fitted, model probabilities, model complexity, and marginal inclusion probabilities. Looking at the histograms for the distribution of the independent variables, I saw that they all have normal distribution except manufacturing output on the bottom left, which has a strong right skew. The descriptive statistics also reflect normal distribution and shows that manufacturing output is normally distributed with some outliers causing the right skew. The histograms prove the variables as statistically significant enough to be used in a predictive model created by multiple linear regression by their mostly normal distribution. The residual plots for the explanatory models are all randomly scattered around the zero and also average out to zero. This means that all the numerical explanatory variables are linearly related to the response variable. The distribution histogram and the residuals QQ plot on the left show acceptably normal distribution with a mean of zero, which satisfies the second condition of a multiple linear regression model. The residuals versus fitted plot on the right demonstrates that the variability of the residuals is equally variable for high and low values of the predicted response variable, as evidenced by the constant width of the band and points being randomly scattered around the zero. In this residuals versus order of collection graph, the independence of the residuals is satisfied as shown by the fact that the points are randomly scattered and do not show a clear pattern. Plugging in values for the independent variables from 2018 into the model, the predicted CO2 emissions are 5.1 metric tons per capita, while the actual emissions were 7.95 metric tons per capita. Clearly, the range in the 95% confidence interval was very wide, and the prediction was not very accurate, but this helped me in creating the Bayesian model. This is the code I used to view the top 5 models with indicators for variable inclusion. This chart shows the ranking of the models from best to worst with rows corresponding to variables in the full model. From the model rank and log posterior odds chart on the left, it is evident that all variables show up in at least 2 of the 5 models, except for manufacturing output, and have marginal probabilities of 0.98 and above. The plot on the right was used in order to examine marginal distributions for variable coefficients. The shape of the curve shows the density of the probabilities for non-zero coefficients. There are no vertical lines that show the posterior probability is 0, so no variables are removed. Here, I used the confident method in order to obtain 95% confidence intervals with the BAS package in R. Using the predict function for the Bayesian model, it was found that the predicted CO2 emissions are 7.697 metric tons per capita, and the actual emissions are 7.95 metric tons per capita. The partial inaccuracy of the multiple linear regression model could possibly be attributed to the strong right skew on the histogram of the manufacturing output. The linear regression analysis did show that a parsimonious multivariable linear model was possible to create and would, to some extent, predict the output of CO2 emissions. The Bayesian model was completely parsimonious and filled all of the Bayesian assumptions and was shown to be highly predictive for China's future CO2 emissions. The model predicted CO2 emissions at 7.697 metric tons per capita, and the actual emissions were 7.95 metric tons per capita. Given projected HDI, manufacturing output, GDP per capita, and population growth rate, it is very effective to use Bayesian modeling to predict future CO2 emission levels in developing nations using economic indicators, as proven in the case of China. This study proves that given projected economic indicators, it is very effective to use Bayesian modeling to predict future CO2 emissions levels in developing nations. There is a new wave of countries that are industrializing, and it is crucial to have accurate models from which to obtain information about the future of CO2 emissions and other direct causes of climate change. While many seem to think that economic prosperity and environmentally sound activity are at odds, it is an impending fact that in the long run, climate change will cripple economies unless action is taken. How economies will have to adapt on the international scale to green policy is also an area for future research. I personally want to go into exactly where economic development and preservative action should compromise in order to create the best standard of living in the long run. For example, I personally want to identify the necessary economic factors that will promote the standard of living while simultaneously stimulating the green market. The world around us is changing in more ways than one. Industry, development, climate. In this critical time, during a fight where the future of the planet rests in our hands, it is of the utmost importance to keep information in our arsenal. Thank you for listening to my presentation.